So, we have started doing the analysis of this SSB-SC, right. The first task is, as we are seeing through the last 2 lectures, that the first task is evaluate the power of the modulated signal, that is the most important part. In SSB we have already seen, if I just put the previous slide. So, what we have seen that modulated signal is mt cos omega ct, up to that it was all fine, but it also has either plus or minus mht sin omega ct or 2 pi f ct. So, evaluation of power becomes more critical over here, because for mt we have a definition, the power I know, but mht we do not know. So, that is why we did some derivation step to actually realize that the power of that, or the power spectral density of mht is same as the power spectral density of mt. Therefore, the overall power, because they are also similarly band limited, so the overall power will remain P. So, now for the modulated signal, if this is P, the corresponding multiplication with cos, that must be P by 2, and if this is also P, the corresponding multiplication with cos or sin, whatever you multiply, the overall power will be again half. So, it should be P by 2. So, P by 2 plus P by 2, it is the overall P power that is being transmitted. So, this is something we could know after doing all these things. So, this ST corresponding power or PS, that is actually P, where P is the way it is defined, MT corresponding power spectral density, if you integrate from minus W to plus W, that is something you get. Okay. So, now we know the power of it at the modulated level. So, therefore, the baseband also must transmit that same power P. Fortunately, here we are getting exact equivalent power. Okay. So, if I just transmit MT, whatever power it will be, that is the same power we are getting. Okay. Now, this is the power we will be transmitting. What is the noise? Again same noise. So, the noise power, that must be, it is a low pass filter from minus W to plus W with strength N0 by 2. So, 2 W into N0 by 2, which is nothing but W N0, right. So, therefore, SNR reference must be P by W N0. Okay. So far it is quite easy. Now, let us try to draw the receiver chain, because now we will have to go through the receiver and then try to see at the output what happens, what is the corresponding noise and what is the corresponding signal power. Okay. So, the receiver chain, if I just draw it, let us do it in a new page. So, that is, let us say WT, which is that signal ST that we have defined, which is a modulated signal, plus noise, this will be incident on the receiver. So, that goes to the receiver. Okay. So, in the very beginning of the receiver, you will have a multiplier. SSB also demodulated in a similar way as DSB is demodulated. So, you will be putting a multiplier, but before that we have to employ a band pass filter. So, this should not be the first part, there should be a band pass filter. Now, the important thing, this particular band pass filter, the band is no longer 2W, because in SSB we have already restricted it to W, because we have taken either the upper band or the lower band. So, the corresponding modulation, whichever way it looks, it will be either from Fc to Fc plus W and minus Fc to minus Fc minus W, or the other way. Okay. One of the band you will be taking. So, therefore, if my interest region is only this, I will be also employing a band pass filter which is only of this width. So, instead of putting a band pass filter of width 2W, I will be now putting a band pass filter of width W, because I want to cancel as much noise I can. If I can do that, why should I waste my this thing, and why should I take some more noise? So, because it is a more spectral efficient modulation scheme, so I know that I can employ a smaller bandwidth filter. Okay. And there is also another thing, what is the central frequency of this particular filter? that is no longer Fc, that is actually Fc plus W by 2. So, this is a big change which happens whenever you employ SSB. So, that filter center frequency is now changed. What will be the consequence of this? The noise will be characterized in a different way, because that is the frequency now of the band pass, that is the central frequency of the band pass noise. So, therefore, if I put it as a in phase and quadrature component, the central frequency will not be omega c, it will be Fc plus W by 2 or 2 pi into Fc plus W by 2. Okay. So, that is the change which will be happening in SSB. Okay. So, all right, I pass through band pass filter. So, what do I get? I will be getting ST will remain as it is, because ST is exactly passing through this filter which is designed for him only. So, therefore, if suppose I call this to be Vt, okay. So, my Vt should be, that should look like Mt. So, St will remain the same, cos 2 pi Fct plus Mht sin 2 pi Fct. So, these two things are there, okay. Plus now the noise part, okay. Noise is a band limited noise. So, therefore, it must have a in phase component, but the corresponding cos should be at this frequency. So, 2 pi Fc plus W by 2 plus Nqt sin 2 pi, sorry, the T was missing over here. Right. So, this must be my Vt, slightly modified because of the filter characteristics. So, means whenever you are doing noise analysis, it is very important that you understand all this process, okay, and you characterize the noise properly. That is the most important part, because otherwise the calculation will be wrong. Okay. So, after that what do we do? After passing through the band pass filter, we will be multiplying by cos 2 pi Fct. Okay. So, this Vt will be now multiplied by cos 2 pi Fct, which is nothing but this Mt will be multiplied by this cos square 2 pi Fct plus Mht sin 2 pi Fct into cos 2 pi Fct plus Nit cos 2 pi Fc plus W by 2 into T into cos 2 pi Fct plus Nqt, that is sin 2 pi Fc plus W by 2 T into cos 2 pi Fct, right. This is what will be happening. Immediately I can simplify this, because this is cos square, I can get half and then I will get two terms, one is Mt and the other one will be Mt cos 4 pi Fct. Similarly, I can also take a half, this will be Mht sin 4 pi Fct, right. So, these are all higher frequency term which will be cancelled by the next low pass filter. Now, these two, it is cos A cos B, if I just take half, cos A plus B plus cos A minus B. So, I can write half Nit cos of A plus B. So, that must be 2 pi into 2 Fc plus W by 2 T plus half Nit. I will have cos A minus B. So, that must be 2 pi W by 2 T, right. I will have this. This is again a higher frequency term, this will be cancelled. Similarly, for sine also I will have, because it is sin A cos B, so it should be sin A plus B plus sin A minus B. So, it should be half NQT sin A plus B means same thing. So, it should be 2 pi 2 FC plus W by 2 to T plus half NQT, this will be sin A minus B. So, that should be sin 2 pi W by 2 into T. This will again get cancelled by the low pass filter. So, after the low pass filter we will be left with half MT plus I will have this half NIT cos 2 pi W by 2 into T plus half NQT sin 2 pi W by 2 to T, right. This is what we get at the output. So, that is my YT. Now, clearly you can see that has a message term and noise term. So, this is the first time, because of this filter central frequency shifted, we get both the in phase and quadrature term in my output noise. Okay. And now we will have to probably get the overall power spectral density of this noise. Now, all those things will be useful, that they have no cross correlation, okay, because if there are cross correlation, there will be cross term which will be generated, but that thing will be, we already know that that is not probably there. It is all event symmetric spectrum and they do not have any cross correlation term, okay, and they are orthogonal to each other. So, basically the overall power spectral density will be just power spectral density of this plus power spectral density of this one. Okay. So, we will have to first evaluate the power spectral density of this one. So, let us try to see what is the power spectral density. First of all, what is Ni? So, this was actually, let us try to evaluate this. So, this was at Fc, this is my N, okay, or SNF I am trying to draw. Okay. So, this was at Fc or minus Fc, and this is at minus Fc minus W. This is at plus Fc, this is at plus Fc plus W, right. So, if I now try to evaluate the Ni, that should be my central frequency, and this will be shifted over here and this will be shifted over here. The strength was N0 by 2, right. So, Ni or N cube will be going from minus W by 2, because it is the central frequency is basically Fc plus W by 2 and that much shift we give. So, therefore, it will be going from minus W by 2 to plus W by 2. So, minus W by 2 to plus W by 2, unlike the previous one, and it goes up to N0, right, they gets added. So, this is my SNIF or SNQF, both of them. Okay. Now, let us just consider this one. Now, NIT is getting a modulated term. So, I will have to first get a modulation term on this. How much modulation? W by 2. So, there will be a shift of W by 2 in this side as well as this side, and because it is a multiplication with cos, so it must be 1 by 4. So, what do I get? So, this N0 will become N0 by 4 and will be shifted to W by 2. So, this will be shifted to W by 2. So, from then it will occupy 0 to W with a strength of N0 by 4 and shifted on the left. So, that will occupy this part, it will come up to W and the strength will be again N0 by 4. So, that should be the spectrum. Is this fine? Ni cos 2 pi w by 2 t should have this spectrum. And why I should consider this whole spectrum? Because my filter, that low pass filter, is having a filter cutoff at w. So, therefore, this entire spectrum as noise will actually enter through the low pass filter. Okay. So, that should be the case. What is the corresponding power? That is actually N0 by 4 into 2W. So, N0 W by 2, fine. You have a half term over here. So, I will get 1 by 4. So, noise due to this, noise power due to this will be this much, fine. Same thing will happen over here, either you multiply by cos or sine. In power spectral you will have no effect. Similar thing will be produced over here, because the frequency is also that shifting frequency or translation frequency is same. So, you will get again, this is actually N0 W by 8, right. So, the other one also will be N0 W by 8. Overall it should be, if I just add these two, N0 W by 4. So, I do get overall noise power which is N0 W by 4. Is this fine? So, this is my noise power. What is the signal power? MT, therefore, it should be P, and half factor is there. In power spectral density it will be half square. So, it should be 1 by 4 P. So, the power is P by 4. So, the signal to noise ratio for SSB must be P, right. Now, the good part, what was the reference signal to noise power? Exactly the same. So, therefore, my figure of merit must be this P by N0 W divided by P by N0 W. Again we get a figure of merit of 1. So, even though SSB is a bandwidth efficient modulation scheme, you will be expecting that probably it will be taking less amount of noise. So, it must be more efficient than DSB-SC, but after the calculation we could see that that is not the case. It is exactly equivalently efficient as the baseband and as the DSB-SC. There is no difference in these two, and both of them are equally efficient compared to our amplitude modulation. In terms of noise analysis, we are just talking about noise analysis, but of course, SSB has other advantage because it uses the frequency in a better way, okay. Because it just with the same frequency it can transmit two signals, potentially two similar kind of signal, because it just takes the half frequency of DSB-SC, right. But we could see noise analysis wise there is no difference. This is a very fundamental result that comes. Generally it is a counterintuitive result, because we expect that because it is more spectrum efficient. So, probably it will, if I employ a proper filtering, probably it will take less amount of noise. So, it must be more efficient. People often also do another mistake while calculating the power of SSB signal. See what people do, you think about a filtering method, okay. So, this is a mistake people often do, of course it should not be done. So, if you just think about filtering method, what happens? Your DSB will look like this, and then as if half the power will be transmitting, okay. What we have seen that SSB exactly transmit P power, whereas if you just calculate it this way, you will think that this is already DSB, so it must be P by 2, and you are transmitting half of that power, so it should be P by 4. That is not the case, okay. Because in a way you have to think that whenever you employ a filtering, you are actually rejecting a band, that means you are wasting the power. So, this P by 2 basically getting counteracted by the filtering. Filter is rejecting that, that means you have to actually generate more power to produce a certain power in the modulated signal. Okay. Suppose you are targeting P power to be transmitted through the modulation process, then you have to actually generate 2 P power over there, then only after filtering you will get P power. So, that is a common mistake I have seen over the years people just do while calculating the power of SSB, they just keep doing this twice halving of power, that they say okay, it is DSB-SC. So, overall power gets half because I am multiplying by cos. I again employ a filter which takes out half of the power. So, it becomes P by 4. That is a very common mistake which people often do. So, we should not do that. And if you do it from the other side, which we have done, you will see that it is actually a P power which is to be launched. Okay. So, this probably end our discussion of noise analysis, because the other thing that can be done, we have also discussed about 2 other modulation scheme. One is quadrature amplitude modulation QAM, and the other one is VSB. VSB it is little bit more trickier, because VSB will not have ideal filtering, and therefore, the noise calculation will not be like that very simple integration. Okay. So, it will have a particular role of filtering, and that filtering has to be considered whenever you are doing that, and accordingly the overall calculation has to be done, because the input filter and output filter for VSB will be typical, and that typical filtering has to be taken into account to actually evaluate the overall noise power that will be linked to your modulation. So, that is something you can take as homework. So, VSB analysis, quadrature amplitude is just almost equivalent to DSB, because it is just 2 DSB simultaneously you are putting, they will have both the noise, and then you just multiply by cos and sine, you have to just see that. So, it will be almost similar to DSB-SC analysis, there will be no difference into that. Okay. So, it will almost be same. So, after doing this, probably we have we told that we will be comparing all these modulation schemes in terms of various aspect. So, now just the one part which was left when we did that comparison chart, that was the noise analysis. Now, we could see the noise in terms of noise, how they perform. So, probably DSB-SC and SSB are the best in terms of noise, whereas AM is not that good noise wise, and VSB you will see that will be little bit inefficient, because you will have a roll off filter. So, that will take additional noise. So, it will not be as good as that. Quadrature amplitude will be similar to DSB, as we have told already. So, it takes means the modulation and demodulation process is almost similar. So, after doing all this, one thing you have to keep in mind, that probably we have said over here that for SSB analysis, we have already told that noise analysis wise it is as good as DSB. There is a gross assumption over here, which probably we have not stated implicitly. We are told that this SSB can be demodulated with a fresh carrier, and we have already seen in our earlier classes that SSB carrier recovery is not that easy. So, therefore, generally in SSB either people add huge amount of carrier like amplitude modulation, because the carrier recovery is not as easy as DSB-SC. So, huge amount of carrier, once you add that, SSB noise analysis also will be as poor or even poorer than your amplitude modulation, because you will have to add a huge amount of carrier to really, and then employ envelope detection. So, it will be similar to that particular process. If fortunately you have carrier by some method, either by transmitting pilot carrier or some other method, because from the signal itself you cannot extract the carrier, because that Hilbert transform and the signal will complicate the carrier recovery process. So, carrier recovery cannot be done as it is, like putting a Costas loop or something like that. So, there you will have to probably, if you wish to do a coherent demodulation, you will have to either put a pilot carrier, or your carrier somehow in a miraculous way should be synchronized. So, that is something which has to be done. Okay. So, we have for our analysis assumed that probably that pilot carrier is available, and that is why SSB is probably looking to be as good as DSB, but that is not the case. We should be always keeping that carrier recovery is a very important circuit, which we have just taken that it is recoverable probably, which is not true. Mathematically we have already proven that. And this completes our amplitude modulation schemes and their analysis, complete analysis. Okay. Now, what we will do from the next class onwards, we will start looking at the another very important modulation, which is called angle modulation, okay, where the amplitude will remain fixed, whereas over here you might have seen that we are just putting all the things, all the message signal in the amplitude of a particular sinusoidal. In the next class onwards, we will try to see that we will keep the amplitude fixed and we will put the message signal in the frequency part or phase part. Okay. Either we will vary the frequency of the sinusoidal with respect to our message signal. So, the modulation will be done at the frequency level, or we will vary the phase part of it and try to modulate it. Okay. So, that is overall these two things are almost similar. You will also means we will demonstrate that. So, you will see that corresponding modulation is called angle modulation, and especially the frequency modulation part is famous as FM or frequency modulation, and phase modulation is called PM, but PM, FM effectively they are almost similar things. The FM will be also able to prove that it has a much better noise immunity. Okay. So, that is something we will try to prove with our noise analysis. Again we will try to give the full blown analysis of FM, means how it performs with respect to noise or in presence of noise, and how it is much better than the AM noise performance. So, that is something we will discuss, and historically probably that is the reason why FM became more important, because it has a better noise cancellation technique, and it survives, means it keeps the quality of the signal much better than AM. So, initially people started with AM historically, but then people could see that FM is much better modulation technique. So, people went to FM, but FM initially was not being accepted in a glad manner by the community. That is because there is a there was initially means a particular doubt in people's mind that FM might have a very huge bandwidth. So, we will also try to do that particular part of analysis, that is really what people have thought, that FM bandwidth is probably very huge whenever we do FM modulation, because the frequencies start varying, and then effectively people initially said that FM probably has infinite bandwidth. We will try to prove that, and we will try to see that probably effective bandwidth is still not infinite, it is band limited still, because if you can only transmit one FM through the entire channel, then it is not good, because all others transmission will be cancelled out. But fortunately that has not happened, and this was mostly proven by a person whose name is almost synonymous to FM, that is Armstrong. So, we will try to see what he could prove and make FM a fundamentally very important modulation scheme in the next class. Thank you.